Okay, so let's get started to the final session. We are on a tight schedule. Mahidhar, I am assuming you are already there.
Yeah, I'm here. And
okay, so just to hold on a few minutes. I'll introduce you, and then you can share your slides. Okay.
Sounds good. Thanks.
Okay, so let's go, and it's a pleasure to introduce Dr. Mahidhar Tatineni. So he received his MS and PhD in aerospace engineering from UCLA. He currently leads the user services group at SDSC, that is the San Diego Supercomputer Center, as a computational and data science research specialist manager. He has led the support of HPC and data application software on several NSF and University of California funded HPC and AI supercomputers, including Voyager, Expanse, Comet, and Gordon, a series of machines at HDSC. He has worked on many NSF-funded optimization and parallelization research projects, such as MPI performance tuning frameworks, hybrid programming models, big data middleware, and application performance evaluation using next-generation communication mechanisms for emerging HPC systems. He has also led tutorials on AI, HPC, and Kubernetes, topics at several PERC and SC conference. He's a co-PI of the NSF-funded Expanse HPC systems and the prototype national research platform, that is a PNRP at SDSC. And he's the PI on the very latest, this category two systems, Cosmos, that will feature the AMD Instinct MI300A APUs that feature both CPU and GPU capabilities. I showed some initial numbers, like in my yesterday's talk. Gautam presented more, but Mahidhar has done much more extensive evaluation. And it's I think we have worked with Mahidhar now, for 15, 16 years now, on all kinds of all these machines, right? Starting from Gordon, Comet, Expanse, Voyager, and also Cosmos. So just like the TAC, OSC also have a long collaboration. OSC, TAC, SDSC. So let's give a big welcome to Mahidhar.
Thanks, DK. And yeah, likewise, very glad to be here and happy that we've been collaborating for so long. Let me get started. So do the slides look okay?
And by the way, Mahidhar, just a quick fact. We had a game night. Mahidhar had come many times earlier to Mug. You remember the game night we do on Monday? The quiz master actually showed this photo. And that was a question saying, where does this is located, this building? Okay. Your computer center photo. That was nice. A quiz question. So those who had visited or have already visited San Diego, they were able to answer very quickly. Okay. But others couldn't do. So it was very interesting. Okay. I just want to share that.
Great. So yeah, the slides look okay, right?
Yeah.
Great, thanks. Thanks, DK. I'll get started. So yeah, as DK mentioned, I'm going to talk about some of our early experiences running with MVAPICH-Plus on Cosmos. It's very early stuff, but I'm glad we got it working, and it's I think in the testbed phase we'll do a lot more benchmarking, I think. So basically the machine Cosmos is an innovative system featuring the MI300A APUs. And as DK mentioned, I'll talk about the MVAPICH-Plus runs on the system. So the system itself, it's a Category 2 testbed system award from NSF. The co-PIs on the project are Subhashini Sivagnanam, Andreas Goetz, Igor Sviligoy, and Christopher Irving. And we have Bob Sinkowitz and Mary Thomas helping out on the training aspects of things. So it's the system itself was aimed at essentially trying to broaden access to broaden the usage of accelerators among like domain scientists and other applications. And the idea was to ease the pathway by enabling codes that aren't yet ported to GPUs. All of the major kind of codes with a lot of development work have been ported, but there's a huge user base that hasn't really gone there because of the expectation that there's a lot of changes needed. So the enabling technology here is the AMD MI300A accelerated processing unit that essentially integrates CPU and GPU capabilities with unified memory. It's a modest size system. It's 42 nodes with 4 APUs per node, so a total of 168 APUs. And our expectation is that the APU memory architecture will facilitate an incremental programming approach so that if someone's changing over their code, they don't have to restructure it completely to use the acceleration available. And the system itself is integrated by HP Cray with HP Slingshot interconnect, and there are 4 socket nodes, and I'll go into the architecture a little bit more further down in the presentation. And it's a fully liquid cooled system. And for the first time, we are also trying out VAST on a production system at SDSC, so that is hopefully going to provide the high IOPS and bandwidth needed for kind of the application workload that we're anticipating. And it's a test bed system, and typically with that, we start with a lot of research collaborations in the first few years, which are more targeted. And we've kind of identified about 20 research groups already that we want to work with, and we'll add more as the test bed phase goes on. So, the main piece of the system is essentially the MI300A chip, which combines CPU, GPU, and memory on one package. There are 6 accelerated compute dies called XCDs that are combined with 3 chiplets that have 8 Zen 4 cores each. So you have essentially 6 of these GPU capable pieces and then 24 Zen 4 cores. And all of them share 128 gigabytes of HBM3 memory coherently between all of them. And there's actually a 256 meg last level cache between the XCDs, shared between the XCDs and the CPU cores. So again, as the hope is that this will eliminate the need to do like host device data copies and make it easier to develop code. Oh, just before I go too far, basically on the right is the image showing the chip, and you can see that there are 228 vector and matrix GPU cores and 24 Zen 4 cores with the HBM3 memory connected. And that's at the chip level, and then at the node level, we have 4 of these chips. And they're fully connected with AMD's Interchip Global Memory Interface, XGMI. And there's 768 gigabytes per second aggregate bidirectional bandwidth and 256 gigabytes per second peer-to-peer between each of the APUs. And each APU is also served by a 200 gigabits per second slingshot NIC. So there are 4 NICs per node. And overall, all of this fits into a single rack of EX2500. We also have a service rack and some storage rack, but basically the main system is this single rack of EX2500 with liquid cooling, fully liquid cooled. So there are 3 chassis per rack and 8 blades per chassis, and each of the blades has 2 4-socket AMD MI300A APU nodes. So that's kind of the layout. And we have node local NVMe on each of the nodes as well. So that's the hardware side of it. On the programming end, we are hoping basically the APU programming model, which will minimize memory movement calls or directives, won't be needed. So basically save the work in porting from a CPU code, for example. And we can port incrementally 1 loop at a time if you want, and interleave the CPU and GPU work. And a lot of programming languages supported, and basically you have the native HIP ROCm approach. You have Pragma-based OpenMP approach, where Actually, AMD has an example of an application ported with this approach with OpenFOAM, which is a very commonly used CFD code. And then you can also leverage for portability frameworks like Cocos and Raja. And we are hoping there's going to be quite a bit of development along all of these lines, because this is, of course, also the chip that's in the biggest system in the world right now. So they are doing a lot of development work, and we actually benefited a little even during the early user and testing period from some of that work. The work up in Livermore. So the compilers, we have GNU, Cray, and AMD compilers on the system with all the Cray MPI and programming environments with profiling and everything that comes with it. Now, we are hoping for using the APU programming model, but that doesn't mean that an application that's written before for an instant GPU kind of setup is not usable. You can pretty much, any applications that are already ported using the HIP and ROCm approach should work. There might be some API calls that are not supported and need a workaround, and I'll give an example of one of these when I talk about the applications. But for the most part, it should work as is. So you're programming it based on the ROCm platform. So you have both HPC and AI-focused libraries, accelerated math and communication libraries, and the compiler suite, and the profiling and debugging, and the Hippify tool, and the driver runtime sit at the bottom of all that. So what would it look like from a programming aspect? So this is a slide I grabbed from the AMD programming page for the MI300A. So they basically, if you have a CPU code that you're trying to use HIP for a GPU code, in the past, you would have had a explicit HIP malloc moving in data, doing your GPU function, synchronizing, and then moving the data out. With the current APU kind of design, you really can cut out the GPU memory allocation, since the pointer is essentially the same, both on the CPU and GPU side. And you don't need to do explicit memory management between CPU and GPU. The sync can still be there, but basically the memory management becomes a lot easier. So the hope is that will make the code porting easier. And this slide essentially summarizes most of what I was saying. So the easier to port, essentially, because even if you have a complex code region, you can basically do that without having to change your memory structure. And the other nice thing is, if you do go the OpenMP offload approach, you can essentially use same code base in a portable fashion. Theoretically, you could use that, like say on a Grace Hopper kind of setup with the same code. Although you might have a slightly different performance characteristic, because there the memory is still a little separate and being managed under the covers, but you still can have similar results. So that's this kind of shows the OpenMP offload approach for basically letting you essentially change at the loop level. But I think I can skip that one. So, so from a Cosmos point of view, we are looking to support a wide range of applications. Our tagline was no code left behind. So we are hoping we can get a lot of codes online. And we already talked to some of the communities that we think might be able to use the APUs. I mean, some of these codes already do have a GPU port and some don't. And we have been working with these groups for a long time. And some of the developers are in our team. So we are hoping we can span a lot of different communities: molecular dynamics, cosmology, neuroscience, like science gateways like ITASR, and so on. And so what's the current status? So that's the system on the floor. and basically showing you the hoses that connect into the liquid cooling on the right there. It was delivered and installed. It was delivered late last year, and kind of HP handed it over to us around late Feb. And we did our acceptance testing and benchmarking, which essentially you can see the codes there, probably the usual suspects for us, like HPL, of course, but then Amber and Unifrac, which was using an OpenMP offload approach, and CGyro, which is a fusion code, and then the IceCube benchmark, which is I think from the Neutrino Observatory, and then we did some standard PyTorch ML kind of testing also. So the review was completed, and we completed our early user phase, and right now we are essentially in the testbed phase. One thing is, when we were doing the initial benchmarks, we didn't really go down the route of porting APU codes and benchmarking them, because that will come in the testbed phase. So in terms of applications on Cosmos, I'll start with some that are, I mean, not involved with MVAPICH-Plus, but just to give a flavor. So one example app is Amber. They already had a GPU port, which was essentially hippified code, CUDA code. And this was one code where we thought, hey, that we already have a AMD version working, and it should be pretty trivial to benchmark, but turns out no, because some of the API calls they were using weren't supported on the MI300A. Luckily, the folks at Livermore had worked on it a little bit already, so we used their modified version. And eventually, since one of the Amber developers is part of the team, Andy, so we will push this into the standard distribution. But just from a benchmarking perspective, we were comparing it to the A100 nodes on some of the performance that we had from before for a couple of standard benchmarks, the Factor 9 NPT benchmark and the STMV NPT benchmark from Amber. It's roughly 2 to 2.5x in terms of performance improvements at a single APU level. Another example is Unifrac. It's like a microbiome distance metric library. This already had a GPU port that was originally based on OpenACC, but Igor, who's one of our co-PIs, had done some modifications to add the OpenMP offload version for this. This worked out of the box. He had actually tested this on an earlier version of AMD GPUs, but this worked out of the box. Again, in terms of performance, it's around 2x of. And then CGyro is a popular fusion simulation tool, and the developers of this code and are also part of our early user experience. So it's got Fortran and vendor FFT and MPI. This we originally tested with the Cray MPI stack, and I haven't yet got to testing it with the MVAPICH-Plus, but we will eventually do that as a comparison. Again, this worked out of the box and showed good scaling going out to 4 nodes. So moving on to MVAPICH-Plus on Cosmos. So Dr. Panda's group, the MVAPICH group were part of basically the early user testing on Cosmos. So they did a lot of development work, and you probably saw the results from them already in the meeting. I actually don't have a lot more than that. I did get to test like one application with this, and so I'll talk about that. So what I was testing was with the GNU compilers and MVAPICH-Plus 4.1. So one of the tricky parts is that the Cray programming environment will already have an MPI integrated compiler. So it actually gets very tricky to build something that excludes that MPI. So I think for the GNU compiler, for example, if you just do a default configure kind of setup, it actually picks up the OS compiler and not the newer GNU version that's in the module. And this is partly because of the way that module works. Like if you load the GNU module by itself and say do a GCC -- version, you'll actually pick up the OS version. It's the magic in the Cray MPI compiler that does the wrapper to pick up the new version of GNU. So that makes it really tricky to kind of compile, like say you are compiling a different MVAPICH version with these compilers, it gets tricky to exclude that. So we are trying to look into workarounds so that we can pick up both versions of this. But for now, the GNU version was working fine, and I was able to test the LAMPS application with that. So it's good, but eventually we want to make the GNU and Cray compilers work, because some applications we've seen work a little bit better with the Cray compilers with the in terms of performance. So that's a to-do in the testbed phase, but today I'll just talk about what I compiled with the GNU compilers. Quick sanity check, OSU benchmark results. You probably saw this earlier, so I'm not going to go into that, but basically looks pretty good from a point-to-point perspective. And then I went on to building lamps using MVAPICH-Plus, and ran into the same issue there too, because the initial build process kept picking up the Cray MPI because I had the environment loaded. And if I didn't have that loaded, I was missing something else. So I was trying to get this to work, and I eventually got it to work with explicit CMake options, which were pointing to the MVAPICH location specifically. And with that, I was able to build two different ways. LAMPS has multiple GPU implementations. Actually, the preferred version, I think, is the Cocos based version. So I built that, and I also built the GPU HIP based package. And those are the CMake options I had to do to kind of wrangle it into shape. But I got that built, and then the testing wise, there's another interesting thing with the way these AMD APUs can be deployed. You can actually expose the 6 XCDs in different fashions. You can have it in a single partition accelerator mode, SPX mode, which is the default on Cosmos, where all 6 of these XCDs combined show up as a single logical GPU device. So if you go look on the node and say do AMD SMI list, it's going to show you 4 GPUs, quote unquote, per node. But you could also run it in triple partition mode, where it divides it into 3 partitions. So you'll have essentially 3 GPUs per APU. So for a total of 12 per node. And there's actually another mod which we didn't try too much because it's not completely supported officially, I think, but it's going to be at some point. So where you can have them as 6 different GPU devices, and you can end up with 24 GPUs per node. So you can already see all the different combinations we can try out. So I tested this in both SPX and TPX mode. The GPU package worked fine, but the Cocos build failed on an initialization, and I think we need some debugging. And this literally happened yesterday, so I haven't had time to give this to the MVAPICH folks to debug and work through, but that's going to happen in the testbed phase. So the benchmark is a pretty standard one, Lennard-Jones potential with 512,000 atoms, and I ran it for a little longer just so that I could see what was going on. So if you look at the LAMPS output in the SPX mode, you'll see it shows up with 4 GPU devices, and you can see the 228 compute units that I mentioned and when I was talking about the architecture. And if you run it in TPX mode, and here I show it with the two APU case, you can see the 6 devices. And you can also see that now the number of compute units is 1/3, so 76 per GPU device. So in the SPX mode, it did pretty well. It's scaling pretty well. I think it can be improved quite a bit, I think, by binding and using more MPI tasks per APU, because I think when I was looking at the utilization, it wasn't really filling the whole GPU. So there's a lot of work we can do, but first glance, everything looks nice and scales. So this is with MVAPICH-Plus. I haven't run this with the Cray MPI for comparisons yet, but all that's coming. And then I kind of did the TPX testing, and actually it was interesting. So and I actually have the A100 result as a comparison just to show that the APU is actually doing pretty well in comparison. If you look at the thing, it's almost 75% faster, I think 1.75x probably. And this is not fully optimized yet, so I expect the number to go up even more. So basically, I was running with only one MPI task per GPU device just as a start. So these are really preliminary results. Like you can easily do more MPI tasks, and there's enough memory to handle the case with multiple MPI tasks. And that's what we did with other applications that I was showing. So it probably explains why the TPX numbers are better, because now when I run 3 GPUs per APU, it also means I have 3 MPI tasks per APU. So you can see that for the single APU result, it's almost more than 2x better than just using one task per APU. With other applications, when we ran with more MPI tasks on the SPX mode, you can come close to the TPX number. So you'll get very similar performance if you can fill up the GPU for the most part. But we did see one strange number, and this is repeatable. I kind of have to see why that was happening. But basically, when I did the full subscription, that is all 12 GPU devices in use, in TPX mode, the performance dropped off quite a bit. Not sure if that's because the MPI layout was not right, or there's some more tweaking to be done in terms of binding and all that. Something to be looked at, but you can see preliminary results looks pretty good in terms of comparisons to like an A100. It's as a starting point. When I did the Cocos-based build and run, the build was fine. I get a good binary, all that looks okay, but it fails with an internal level MPI error. And I haven't had a chance to give this to the MVAPICH team yet, but I will, and we can follow up. It's an MPI weight that's failing for some reason. And I haven't tested it with the Cray MPI compilers as well. As you know, both of these MPIs have the base as MPICH. So it might end up with the same error. So I have to go try it out and see what comes up. So that's essentially the extent of what I've tested with MVAPICH-Plus so far. Good promising results as like early testing. It's barely a week of testing from my side yet. So there's going to be a lot more numbers coming. Just a quick note on AI ML applications. AMD provides both the PyTorch and TensorFlow packages already optimized, including for MI300A. You can do both Docker containers and pip installs. Really don't need to change anything in the user code. And one of the applications we tested was essentially like a spatial temporal forecasting ML training example. That's kind of one of our early users. Research groups, their test case essentially. And it was almost 3x faster than the A100, so doing pretty good on the performance aspect. Again, scaling and training with more multi-node and going out is something I'm thinking of trying with both the MVAPICH-Plus and the Cray MPIs. So just to summarize, it's basically a highly innovative architecture APU, the MI300A. Cosmos will be the first one to introduce this to the NSF community. And we'll hopefully enable a lot more people use accelerators. And early results from MVAPICH-Plus are promising, and we're going to continue testing. Thanks to a lot of the co-PIs and many others at SDSC who contributed to the proposal and just making the machine happen. As you can see, the machine room underfloor, you needed a lot of work because of the cooling infrastructure and all that. So all that, a lot of thanks to everyone to get that done in time and get us through the reliability and into production. So, and thanks to Dr. Panda's group and the MVAPICH team, I think we keep throwing all kinds of innovative hardware at them, and somehow they come up with performant MPI versions for everything. So that's always been nice. I think over decades of collaboration. So it's a great team, and hopefully we'll continue with that work. Thanks.
Thanks. Let's give thanks to Mahidhar. Yeah, so Mahidhar, let us know what the error you are seeing, and we'll be happy
Yeah.
to take a look. We have not run LAM APS, but Gautam will follow up and then.
Yeah, definitely.
Are
I will.
okay.
Yeah.
Are there any questions from anybody here? Yes, Gautam, go ahead.
Yeah, thanks, Mahidhar. This is a great talk. This is Gautam here. So I'd like to know, are there any profiling tools available on Cosmos?
Yes, so the Cray stack comes with the usual Cray pat and all the profiling tools, and AMD I think has tools that might be specific to MI300A also. So I haven't yet explored that, but will be in the next week or so, because I'm going to be doing a talk at ICPP, and part of that we will go into the profiling aspects. So yes, definitely there are tools, and we can discuss that.
Yeah, thanks. So the other question that I have, quickly I'll ask that. So there are like 6 XCDs and 8 stacks of HBM, right? Is there a way to force the allocator or know where the memory is exactly being allocated?
So when it's in the combined as one single GPU, unfortunately not. You really can't do that. From what I know from AMD, talking to AMD,